Welcome in everyone. In this video I'm going to cover the chain rule. First I'll go over what it is and why it's important. The next thing I'll go over is how to decompose functions, and we'll do some examples of that. And then we'll get into some examples of the actual chain function or chain rule in action. Let's get into it. So on this slide, we're going to go over what the chain rule is and why it's important, but first, why it's important. It's the rule that allows us to take the derivative of a composition of functions and really does open the door to take very complex derivatives, especially when you combine it with the product and quotient and power rule. So what does the chain rule say? Well, if you have a function y equaling f of u, and it is a differentiable function of u, and you have a function u, that same u up here, equal to g of x, and that is a differentiable function of x, then y equals f of g of x, which you can see by substituting g of x in for u up here. This whole expression then is a differentiable function of x. And we have these two conclusions down here. This is the math behind it. We can say dy dx equals the derivative of y with respect to u times the derivative of u with respect to x. Or, if you like to think of it in function notation, the derivative of f of g of x equals f prime of g of x times g of x. And another thing that I'll say in this video quite frequently is we will talk about the inside function, in this case g of x, and the outside function, aka f of x. And I'll say quite frequently the derivative of the outside function, leave the inside function alone, times the derivative of the inside function. Now that you've seen what the chain rule is and why it's important within the context of math, let's go over how to decompose functions. And what we're going to be doing is we're going to be looking at a function like this or any of these, and we're going to try to figure out what the inside and what the outside functions are. One rule you must follow is that neither of these functions can be the identity function, aka just the letter x. They can't be the letter x. So we're going to have to get a little more creative with it. All right. One of the really big indicators of where the inside and outside functions are is really first trying to find the inside function. And in this case, in the very first example, we can just see what's inside the parentheses. And inside the parentheses here, we have 2x minus 7. That's what we will call our u, our function u in terms of x. From there, we just have to substitute. Instead of 2x minus 7, we're going to put u in its place. Because when we come over here and write our y function, our y has to be in terms of u. So u to the 13th power, it would be 2x minus 7 in parentheses to the 13th power if we substituted this in for u. And that's basically how the rest of these are going to work. We just need to find the inside function and the outside function and be done with it. Do that little decomposition. For the next example then, h of x equals the fourth root of 3x squared minus cosine x. You can pretty easily see that the 3x squared minus cosine x is what's inside of the root. Then we can say that y equals the fourth root of u, which I want to remember or bring back that 1/4 power is the same thing as a fourth root. And for p of x equals negative 7 all over 2x plus 1, the quantity to the 4th power, you can still pretty easily see that u is inside the set of parentheses 2x plus 1 and then y will equal negative 7 over u to the fourth. And look at how much simpler finding the derivative of this is now. You can find the derivative using the power rule here. You can find the derivative using the power rule here. Everything we've looked at is either a trig function or a power rule after we've decomposed. Trying to tackle these right as you see them is a lot more daunting without decomposing them. All right, and the inside functions do extend over to trig functions. So in this case, the inside function is tangent of x, but then the outside function is going to be cosecant of u. And you can see that again, if you take this tangent of x, that's what u is equal to, and substitute it in here, we would get what we started with. Now the only one here that might cause problems is this last one, cosecant to the fourth power of x. This is a little bit tricky because the cosecant is the inside function here. That's because you can rewrite this as cosecant of x to the fourth power. That's what this fourth power is telling you right here. So now cosecant of x is the inside function, and u to the fourth power, or raising to the power 4, would be the outside function. And these are not the only examples you'll see of this. As we move through the examples of the actual chain rule being applied to functions, you'll see more composition or decompositions to make finding the derivatives easier. For the first example in this video, we are simply going to be asked to find f prime of t if f of t equals this function. Now, if we can decompose it, this will be done fairly easily. So what I intend to do here is use decomposition to find the inside and outside function. Using the methods from the previous slide, I know the inside function is 9t plus 2, and the outside function is basically everything else, 1 over u, because that's what u is equal to, 9t plus 2, to the 5/6 power. Once you have the decompositions, this derivative can very easily be found by using the differential notation that we learned, dy dt in this case, because that's the variable we have, will equal the derivative of y with respect to u times the derivative of u with respect to t. In the theorem, there are x's here because we assumed g of x was in terms of x. All right, so let's take the derivative of y with respect to u, but first recognizing that this is u to the negative 5/6 power. Once you have that, you can see that dy du will be negative 5/6 u to the negative 11/6. And if you rewrite that, it's negative 5 over 6u to the 11/6. So there's our first part of the derivative. This is negative 5 over 6u to the 11/6. And we're going to multiply that by the derivative of the u function. Thankfully, this is just a polynomial. We can do that pretty quickly. The derivative of u is just going to be 9. Now, we are taking a derivative of y with respect to t. So everything over here should be in terms of t, which means u should not be u, but u should be 9t plus 2 because that's what we found was the inside function. So the final derivative here will look something like this. All right, and you can see we've preserved the variable we've started with being t because we made that final substitution here. And again, in this form, we took the derivative of the outside function, there it is. We left the inside function inside of it, right? We didn't take a derivative here, but what we did was we multiplied by the derivative of the inside function out back. And yes, you can simplify this if you want to negative 15 over 2 times 9t plus 2 to the 11/6 power. Just simplifying the 9 with the 6 and then multiplying that 3 times negative 5 to get negative 15 on top. When a 3 canceled here, we have a 2 in the bottom. Okay, let's go on to the next example. For the next example, if y equals t squared over t cubed plus 2, all of that being raised to the 5th power, find dy dt. So again, we just need to decompose this. There we go. So you can see the inside function here is t squared over t cubed plus 2, and the outside function is just that, u being raised to the 5th power. So honestly, since we're going to be taking the derivative of these, I'm going to do this one first because dy du is going to be easy enough. That's 5u to the 4th power. But taking the derivative of u with respect to t is going to require the chain rule. So I will slowly release some steps up here on how that looks. So here is the simplified version of the quotient rule being used here to find the derivative of u with respect to t. Now all we have to do is write out our differential notation, dy over du times du over dt. So let's go ahead and do that. This will be dy dt. So the dy du derivative up here is 5u to the 4th, but we already know that we're going to have this in terms of t because that's how we started. So I'm just going to substitute this fraction back in for u as I write this out. So 5 times t squared all over t cubed plus 2 to the 4th power. From there, we can multiply by du dt. So that will be negative t times t cubed minus 4 all over t cubed plus 2 to the 2nd power. And this can be simplified, but this is a very good, respectable answer. I forgot I put this example in here. Okay, in this example, we're going to be trying to find the derivative of this function. And a couple differences between this function and the previous examples functions are this function has many nested functions inside one another. The other thing is we introduce the first function with trig. So the process still holds the same. We're going to have an inner and outer function. So that means I'm going to have an outer function that is y equal sine of u. And you can see here that this is u. That's what's inside the function. So I'm going to go ahead and write that down. U equals cosine of tangent of pi theta. But here you can see that we also have an inside function for this one, which I'm going to go ahead and call v. So we can rewrite u in terms of v. U equals cosine of v, where v is the tangent of pi theta, And since this is not only the variable in here, something else is operating on the variable, we have to do this one more time. So we can call this W, which means now that V equals tangent of W, and W equals pi of theta. All right, well, that's quite a few chain rules. What's happening here? Well, I'm going to put some parentheses and then I can explain. Here, what we have is we have many steps to get through this. So we want to take the derivative of y with respect to theta, but first we're going to have to take the derivative of y with respect to u. Then we're going to have to multiply that by the derivative of u with respect to v. Then we're going to have to multiply that by the derivative of v with respect to w. And finally, since there are no more inner and outer functions here, we're going to take the derivative of w with respect to theta. And it's almost like you can think of these as canceling out. du would cancel with du, dv would cancel with dv, dw with dw, and you'd be left with a dy d theta. But really what's happening is we have to take the derivatives with respect to all these other variables in order to make it work. On the next slide, we'll go ahead and finish this up. So just considering the equations that relate all of the variables together, we can easily find the derivatives of these. dy du is cosine of u. Du dv is negative sine of v. dv dw is secant squared w, and of course dw d theta is just pi. So it's good to know that this is what we're working with, and we can go ahead and write all this out, right? It's dy du times du dv times dv dw times dw d theta. But this w, v, u, we need to have all of those in terms of theta. So I hope you were taking notes from the last slide. If not, go find what those functions were. But that means the final derivative here would be dy d theta equals, this would be cosine of u, and u from the previous slide was cosine of tangent of pi theta, multiplied to du dv, which is negative sine of v. V was just tangent of pi theta, times dv dw, which is secant squared w. But w, remember, you can see here, was just pi theta, so we've got to have pi theta in there, times dw d theta, which is pi. And yes, this was a fun example for me, but if you're watching this and you're learning this for the first time, you're probably freaking out a little bit. I would like to assure you that most chain rule within chain rule examples will only be 2 chain rules deep. It will rarely ever go to where you're running through 4 different chain rules to find a derivative. But it would make for a nice bonus question. Okay, back to an easier example. Let's find the equation of a tangent line. Haven't done that in a while. Let's find the equation of a tangent line at 2, 2 for this function. So with this function, we can see that it's 1/4 x times this. So I think, pretty sure, we're going to have to use a product rule here. So let's go ahead and write out the product rule, and I'm going to write it out a little bit differently than I normally do. So I'm going to go ahead and say f prime of x equals, I'm going to call this my u, I'm going to call this my v. So I'm going to say it's the first, aka u, so 1/4 x times the derivative of the second, but I'm just going to write it like this here. The derivative of square root of x squared plus 12 plus the second square root of x squared plus 12 times the derivative of the first d dx 1/4 x. All right. So what happens here then is when you write out the product rule by needing to take derivatives, right? I haven't taken any derivatives yet. No calculus has actually happened. The derivatives are here. So I have to take the derivative. This one just uses power rule, so it's 1/4. This one, however, is going to need a chain rule. So the chain rule here, you can see the inner function, you can see the outer function. So let's figure that out really quick in some other colors. So here we have the inner function, that's u. The outer function is the square root. It's the 1/2 power. So all at once, I can say something like it'll be the derivative of the outer function, so 1/2 times, leave the inner function alone, negative 1/2, times the derivative of the inner function. And there, that's one-step chain rule. Everything else comes along for the ride. So we've got a plus, we've got a square root here, x squared plus 12 times 1/4. That was the easy power rule there. All right. From here, we can combine things and move things around as needed. So in the first term here, the whole first term, there we go. It'll end up being a 2 canceling with a 2, and the x will go to the top. So we'll have an x over x squared plus 12 to the 1/2 power plus square root of x squared plus 12 all over 4 for the second term. And some professors out there may make you simplify this, and that's fine. You can just recognize that 1/2 is the same thing as square root. Basically, this numerator and this denominator are exactly the same. Simplifying in this case means having only one fraction instead of 2, so you'd have to find a common denominator here. In this case, it would be 4 times x squared plus 12 to the 1/2 power. So you would multiply top and bottom here by 4, and you could multiply top and bottom here by square root of x squared plus 12. And so you'll end up with something like this, 4x plus x squared plus 12 all over 4 times x squared plus 12 to the 1/2 power. And then you can rewrite it so that it's nicely written out there, x squared plus 4x plus 12 all over 4 times x squared plus 12 to the 1/2 power. And again, I want to point out, this is just a simplified version of this. And just depending upon what your professor is asking or teacher is asking, just make sure you know how to get from here to here. All right, last example for the video. We're going to find the second derivative for this function. So here you can see we have this weird instance of the trig function where this square applies to the entire secant function and everything inside of it. So I'm just going to rewrite this as secant pi x to the second power. And as I mentioned, most embedded chain rules will only go 2 levels deep. That is the case with this one. So pause the video, use the chain rule, see if you can find the first derivative, and I will put the answer up here in about 5 seconds. Hopefully you got something like this. The square got moved down, right? Take the derivative of the outside function, leave it inside alone. So it became secant pi of x. From there, we take the derivative of this inside function. Secant pi x becomes secant pi x times tangent pi x. Then there was another inner function there of pi x. So the derivative of that was pi. And we can rewrite this with the 2 pi out front if you like. And in fact, I'm going to do that because this simplifies nicely. 2 pi times secant squared pi x times tangent pi x. And of course, this is only the first derivative. So now we are going to go ahead and find the second derivative, which involves a product rule this time. So this will feel a lot like the last example, but with trig. Okay, thankfully, we already know what the derivative of secant squared pi x is. So let's use that to our advantage when we go through and complete this second derivative. So the second derivative is equal to 2 pi, and we're just going to leave that out front because that's a constant being multiplied here. We can say first times the derivative of the second. So secant squared pi x times the derivative of the second function here, tangent pi of x, which actually has a sneaky chain rule here, right? Because this inner function isn't just x, it has an operation happening to it. So the outer function here is tangent. The derivative of tangent is secant squared. Leave the inside alone. Take the derivative of the inside function. So that is the first half of this product rule. The second half of this product rule is the second function times the derivative of the first. So that would be times, remember we said this is the derivative of secant squared pi x. That's what we're taking the derivative of again. So at least we already know what it is. We just have to work on squeezing it on screen. Tangent pi x. Yeah, I think that does it. Oh, forgot a squared. There we go. From here, this derivative is fine by me. I'm going to clean this up a little bit. I'm going to do some factoring because I realize I can take a secant squared pi x and a pi out of each of these terms. I can combine these tangent pi x's here, and I can have the secant squared alone in that first term. So here's what the second derivative will look like. 2 pi squared, because we're bringing that pi out. Secant squared pi x times whatever's left over after we do the factoring. Plus 2 tangent squared pi x. All right. Again, just based on whatever your professor's looking for, I'm okay with this top answer. Simplifying is not everybody's bag of tea. I do enjoy that as well. So for anybody who needed to simplify it, this would be a good simplified answer. I hope this video helped you out.